Let's imagine a world made of countless islands, each one thriving on its own. Some islands are advanced cities, buzzing with commerce and innovation. Others are quieter, focused on a single craft or resource. Now, picture these islands existing in complete isolation. A city filled with ideas can't trade with a farming island that has abundant food. A medical island with life saving herbs can't reach the cities that desperately need them. That is how blockchains used to operate, powerful but isolated. Now imagine if instead of relying on fragile bridges or risky makeshift ferries, there was a seamless system of ships, planes, and instant communication lines. An invisible technology that allowed every island to interact freely, trade securely, and share knowledge without barriers. That invisible web of connectivity is what we call Layer Zero. It's not beneath the islands and it's not above them. It is the infrastructure that makes collaboration possible. In this video, we're going to explore Layer Zero blockchains and protocols, the foundations that make multi-chain ecosystems possible. And to do that, we'll look at some of the most influential projects like Polkadot, Cosmos, Celestia, Avalanche, and LayerZero. With each, we'll explain how they handle networking, consensus, cross-chain messaging, data availability, and security. Before we understand what LayerZero does, let's remember the challenge it was built to fix. In the early blockchain era, every chain was an island with its own language, economy, and governance. Bitcoin was built for peer-to-peer payments. Ethereum became the hub for smart contracts. Others followed, each with innovations, but none that could naturally talk to the rest. This fragmentation meant value was trapped within silos. Developers had to choose one ecosystem and stay there, even if a better tool existed elsewhere. Bridges emerged as a temporary fix, connecting these islands through makeshift wooden walkways. But as history shows, bridges are fragile. Many were hacked, exploited, or overloaded, costing billions in lost funds and eroding trust in cross-chain interactions. Users wanted the freedom to move assets, data, and identity across blockchains, but without risking everything each time. And beneath that, there was another issue: scalability. Each blockchain had to handle its own consensus, security, and data availability, a heavy load that slowed down innovation. What if there was a base layer that could provide these services universally, allowing blockchains to focus on what they do best? That's where Layer Zero comes in, the silent infrastructure that replaces the shaky bridges with a solid, invisible network. A layer that connects chains natively, enabling them to scale together and share security and communication seamlessly. So what exactly is Layer Zero? If you think of Layer 1 as the island, the blockchain itself, where applications and tokens live, then Layer Zero is the ocean that connects every island using infrastructures like ships, bridges, and ferries. It's the foundation of interconnectivity, the layer that provides the networking, consensus, data availability, and cross-chain messaging infrastructure for all the blockchains built on top of it. Unlike traditional layers, Layer Zero doesn't compete with blockchains. It empowers them. It's the reason blockchains no longer need to exist as silos. It makes it possible for value on one chain to be used by an application on another, for messages to flow securely between networks, and for developers to create multi-chain ecosystems that feel unified rather than fragmented. In essence, Layer Zero transforms the blockchain landscape from scattered islands into a connected archipelago, a world where collaboration is not an afterthought, but the foundation. We'll start with Polkadot, which is often described as the Internet of blockchains, and for good reason. At its center is the relay chain, the hub that connects a web of specialized blockchains known as parachains. Think of the relay chain as a central harbor and the parachains as unique islands, each building ships that can dock into that harbor and instantly communicate with the others. What holds this network together is its nominated proof-of-stake consensus model, which balances power between validators and nominators. Validators are responsible for producing and finalizing blocks, while nominators support them by staking tokens, ensuring only trustworthy validators are chosen. Together, they secure not just the relay chain, but every parachain plugged into it, meaning even a small emerging chain can rely on the strength of the entire network. But a network is only useful if its members can communicate. That's where Polkadot's cross-chain message passing XCMP comes in. Messages between parachains travel directly through secure channels, preserving order and reliability, almost like sending sealed letters between trusted embassies. This system allows applications across parachains to interact seamlessly, whether transferring tokens, sharing state, or executing cross-chain logic. Data availability is equally crucial. To ensure no parachain hides invalid transactions, relay chain validators check and validate parachain blocks. By distributing this responsibility, Polkadot ensures transparency and prevents censorship, giving every participant confidence in the system. Ultimately, security in Polkadot is collective. By joining the relay chain, each parachain inherits the security of the entire validator set, creating a model where the whole is far more secure than any of its parts alone. While Polkadot focuses on shared security, Cosmos takes a different path: sovereignty. Imagine not one central harbor, but a system of airports where every island controls its own runway, but follows the same flight rules so they can travel to each other freely. Cosmos envisions a world of independent blockchains called zones, all connected through the Cosmos Hub and its inter-blockchain communication protocol, IBC. At the heart of Cosmos lies the Tendermint consensus algorithm, which uses Byzantine fault-tolerant proof of stake. It's fast, deterministic, and energy efficient, allowing zones to finalize blocks in seconds. This speed ensures that when zones communicate, they do so without delay, maintaining trust across the network. Communication happens through IBC, which standardizes how zones send data. Think of it like international air travel, where every plane and airport follows common protocols for safety and reliability. With IBC, Cosmos zones can transfer assets, share information, and build interconnected applications without needing centralized bridges. Unlike Polkadot's shared security, Cosmos gives each zone responsibility for its own validator set and data availability. This autonomy means zones can design their own security models, some highly decentralized, others optimized for speed. The trade-off is flexibility versus collective protection. Yet security in Cosmos is evolving. With innovations like interchain security, the Cosmos Hub can lend its validator power to smaller zones, offering them stronger guarantees without taking away their sovereignty. This balance between independence and collaboration is what makes Cosmos unique. Celestia takes a radical approach by narrowing its focus to data availability. Instead of being a hub for many blockchains, Celestia acts as the shared infrastructure that ensures every transaction in a blockchain is visible, accessible, and verifiable. Think of it as a massive public library where every island must publish its records, ensuring nothing is hidden or forged. Its networking layer is optimized for distributing data across many light nodes. These light nodes don't need to process every transaction themselves. Instead, they perform data availability sampling, randomly checking small portions of the data to confirm that the whole dataset exists. This approach makes it extremely scalable, allowing many blockchains to rely on Celestia without overburdening the system. Consensus in Celestia is achieved through a proof-of-stake mechanism ensuring blocks of data are finalized securely. But unlike other layer zeros, Celestia doesn't care what your blockchain logic is, it only guarantees that your data is available. Execution is left to the rollups and blockchains that plug into it. Cross-chain communication in Celestia doesn't happen directly. Instead, it supports ecosystems like rollups to build their own messaging layers, all while relying on Celestia to make sure the data is transparent and accessible. Security in Celestia comes from decentralization and transparency. Because light nodes can cheaply verify data availability, it's very difficult for malicious actors to hide fraudulent blocks. This shifts power away from a small set of validators and into the hands of the wider network, enhancing trust across the ecosystem. Avalanche approaches LayerZero with a focus on speed and customization. Its architecture is built around subnets, independent blockchains that can be customized for different use cases, yet all connected through the Avalanche platform. Picture an archipelago where each island can govern itself, but they all share the same transportation system that makes travel fast and efficient. Avalanche's consensus mechanism is what makes it remarkable. Rather than traditional proof-of-stake voting, it uses repeated random sampling. Validators query a small, random group of peers about the validity of a transaction. As these queries ripple through the network, the system quickly converges on agreement, like a crowd of people rapidly reaching consensus by asking their neighbors. This process makes Avalanche capable of finalizing transactions in less than 2 seconds, one of the fastest in the blockchain world. Networking between subnets is efficient but somewhat isolated. Subnets can set their own rules and validator sets, giving developers freedom. However, they all settle through the Avalanche main network, ensuring a base layer of coordination and consistency. Cross-chain communication within Avalanche happens across its 3 primary chains: the X chain for assets, the C chain for smart contracts, and the P chain for staking and governance. These chains work in tandem, and subnets can interact with them, creating a dynamic balance between independence and shared infrastructure. Data availability is handled within each subnet, giving developers flexibility, but also placing responsibility on them to design robust systems. Security, meanwhile, is anchored in the Avalanche validator set and its unique consensus. Because it requires large-scale participation to attack, the system remains resilient while offering unmatched performance. LayerZero takes a different role in the LayerZero landscape. It's not about building blockchains, but about connecting them. It's an omnichain messaging protocol designed to let applications communicate across blockchains as if they were on the same network. Think of it as the fiber optic cables connecting our islands, allowing not just trade or travel, but real-time conversations. At its core, LayerZero deploys immutable endpoint contracts on every supported blockchain. When an application wants to send a message, it writes to the endpoint on the source chain. That message is packaged and verified by decentralized verifier networks before being delivered to the endpoint on the destination chain. The receiver contract then processes it, executing the intended action. Networking in LayerZero is channel-based. Each application establishes its own channel with unique identifiers, ensuring messages don't get mixed up. Nonce tracking guarantees that messages arrive in order and only once, like carefully numbered telegrams sent between offices. Consensus and security in LayerZero are modular. Instead of relying on one global validator set, each application can configure its own security stack, choosing from decentralized verifier networks to match its needs. And this flexibility allows applications to optimize for speed, cost, or security depending on their goals. Cross-chain messaging is where LayerZero shines, from transferring tokens across chains to querying state, or even composing complex multi-chain workflows. It provides the primitives developers need to make their applications omnichain. Data availability, in LayerZero's case, depends on the blockchains it connects. Its role is to ensure messages move securely and reliably between them without dictating how the chains themselves store or validate their data. By decoupling execution from messaging, LayerZero creates a flexible framework that applications can adapt to any environment. LayerZero is not about being beneath blockchains, it's about being between them, the fabric that makes true interoperability possible. Whether it's Polkadot's shared security, Cosmos's sovereign zones, Celestia's data availability layer, Avalanche's high-speed subnets, or LayerZero's omnichain messaging, each project represents a unique approach to solving the puzzle of blockchain connectivity. Just like our islands, blockchains are far more powerful when they're connected, and as these LayerZero protocols continue to evolve, they're laying the foundation for a truly unified global decentralized network, one where information, assets, and ideas can move as freely as the people who use them. If you've learned from this video, please hit the subscribe button for more videos like this, and don't forget to like and share the video. You can drop a comment if you have any questions. Thanks for watching, and I'll see you in the next video.